Hello there. In this video we're going to discuss what is often referred to as Euler's theorem and sometimes often referred to as the Euler-Cotes theorem. So in the previous videos we've discussed various types of power series and Taylor series. One of them being sine of x is equal to x minus x cubed over 3 factorial plus x5 over 5 factorial minus x7 over 7 factorial plus minus and so on. Another series is cosine, which is similar, just even alternating powers, namely 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus minus and so on. Another more common series would be e to the x, which we know as 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial plus and so on. So what the Euler-Cotes theorem does is combine these three identities into one simple formula. And that's what we're going to discuss in this video. So to begin our discussion, we're going to recall a very basic complex number from pre-calc, namely I is equal to the square root of -1. So let's review a couple properties about this. So if I is equal to the square root of -1, I of course is equal to I, which is the same as I to the first. I to the second is going to be -1. I cubed is going to be -I, and I fourth is going to be equal to 1. If we continue in this fashion, we have I to the fifth is equal to I to the sixth is going to be equal to -1, I to the seventh will be -I, and I to the eighth will be equal to 1. And you can generalize this for all multiples of 4, modulo 0, 1, 2, and 3. But we're not going to generalize that here. I reference you to another video where we discussed that. So I'm going to consider from our Taylor series of e to the u, which in this case is 1 plus u squared over 2 factorial plus u cubed over 3 factorial plus u4 over 4 factorial. And what I'm going to do is I'm going to let u be equal to ix. So once we make that substitution into all of these representations of u, we get e to the ix is going to be equal to 1 plus ix plus ix squared over 2 factorial plus ix cubed over 3 factorial plus ix4 over 4 factorial plus ix5 over 5 factorial plus and so on. So I'm going to use these powers of i's here. So I squared, I cubed, I4, I5, and so on. And I'm going to sort of see if I can see a pattern here. So e to the ix is going to be equal to 1 plus ix. So I squared is -1, so this becomes minus x squared over 2 factorial. So I cubed is -I, so I have minus I x cubed over 3 factorial. I fourth is going to be equal to 1, so this is just going to be plus x4 over 4 factorial. X to the fifth, I to the fifth is the same as I, so we can rewrite that as I times x to the fifth over 5 factorial, and we can continue this on for all of the other powers. What I'm going to do is I'm going to group all of the terms that do not have i's in them. So 1 minus x squared over 2 factorial plus x4 over 4 factorial. So minus x to the 6th, so maybe I should rewrite this next term as minus plus and so on, is going to be minus x to the 6 over 6 factorial. So we have e to the ix is equal to 1 minus x squared over 2 factorial plus x4 over 4 factorial minus plus and so on. And then I'm going to factor out an I out of all these other terms, and I'm going to be left with what? So I'm going to have x minus x cubed over 3 factorial plus x5 over 5 factorial minus plus and so on. So what are these expressions in these parentheses? or this is precisely cosine, and this is precisely sine. So we get the magic Euler-Cotes formula as e to the ix is equal to cosine x plus I times the sine of x, where I is the square root of -1. So cosine, sine, and exponential functions are pretty much the same exact thing, in the complex plane, of course. And that may need a little bit of time to sort of let that sink in. So let's do some examples of some consequences of this relationship. So example 1. Suppose I ask, what is e to the I pi equal to? So I'm pretty much going to let x be equal to pi in this relationship. So that's going to be equal to cosine of pi plus I times the sine of pi. And if we go back to our unit circle, so pi is going to be located over here. So that point is -1, 0. So cosine is the x value, sine is the y value. So that means e to the I pi is going to be equal to, so the cosine is going to be -1 plus I times the sine of pi, that's going to be 0. So the imaginary part disappears. So I'm left with e to the I pi is equal to -1. And this also gives birth to a very famous identity, which some people refer to as the most beautiful formula in math, namely e to the I pi plus 1 is equal to 0. So you get this very elegant, simple property. So a couple examples. So example 2. What about e to the 3 pi over 2 to the power I? So using the Euler-Cotes relationship again, we have this is going to be cosine of 3 pi over 2 plus I times the sine of 3 pi over 2. So where is 3 pi over 2? So 3 pi over 2 is going to be located down here, which has a value of 0, -1. So cosine of 3 over 2 is 0. Sine of 3 pi over 2 is going to be -1. So we have that e to the 3 pi over 2i is equal to I times -1, or -I. And you can do the same exact procedure for any values theta for which the values of sine theta and cosine theta are known. So let's also derive another formula, so example 3. And this formula is sometimes referred to as de-moivres theorem. So we're going to consider the expression cosine of theta plus I sine of theta, all raised to the power n. So we already know that this expression here is the same thing as e to the I theta. So we can rewrite this as e to the I theta, all raised to the power n. So power to a power we can multiply. So this is going to be the same as e to the I n theta. And then we can use the Euler-Cotes relationship on this expression where n theta is equal to x. So therefore, cosine of theta plus I sine of theta, all raised to the power n, is the same thing as cosine of n theta plus I times the sine of n theta, which is a very interesting relationship because now we have exponents turning into coefficients inside of cosine and sine. So definitely the Euler-Cotes relationship shares very unique and interesting properties that sort of connect cosine, sine, and exponentials. But definitely the conversation here is just a short introduction to these connections, but I definitely invite you to explore what other properties will come out of this.